Yeah, as the introduction said, today is all about long-lived nuclear spin states and applications. I've been told this series here is part tutorial and part application. So I'm gonna split the talk in two parts. So in the first part, I will discuss a little bit about the states, and then I would like to show which kind of application were developed over the years, and also how we are using this in my group to understand, to basically find out information about molecule structure and things like that. So we will see the details in a minute. So, so I'll start with this prologue about long-lived spin states. And obviously there is a different ways to say this. And I still find this way here probably the most instructive. So let's take like a spin pair, like two spin and a half, which are coupled together. And we all know there are like 4 energy levels. And these 4 energy levels, they are interconnected. So you could realize transition between the move population around through connection given by the internal Hamiltonian terms in liquid states, basically J coupling and chemical shift. And also relaxation mechanisms connect these states. So relaxation can scramble population around in these states. And the relaxation is often seen as the states are connected to the molecular environment, so they exchange energy with all the rest of the molecules surrounding your spin system. And this happened due to a series of mechanisms, which here I isolate one in particular, the dipolar relaxation mechanism, DD, and all the other, they fall into the category other mechanism. And we will see those in details in a second. And eventually, all what is done, it will discharge a non-equilibrium population you create among these 4 states with a decay constant, which we all know, we all call T1. Well, then the thing is this. Suppose we make some changes in either in a magnetic or electronic environment of this spin system, we could see the same 4 spin state grouped in a different way. We have a triplet state, so 3 states which are still interconnected by the internal Hamiltonian and the relaxation mechanisms. So in some sense, they relax to the molecular environment with the same decay constant, again, T1, and then down here. And then a single state, which we call singlet, which is connected with the triplet state through the difference in chemical shift between the 2 spins in the pair. But if we manage to actually suppress this difference in chemical shift, then we also have an isolated long spin state who is immune to the dipolar relaxation mechanisms and is only connected to the lattice through other mechanisms. And there is an asterisk there because this other mechanism, the connection to the other mechanism, is different and often more convenient to us than the way the triplets are connected to the molecular environment. So in other words, these states decays so the population discharges into the triplet one much slowly than the T1. So in that sense, we call them long-lived. Now, if we isolate the other mechanisms, then there is a plethora of those which have been known to the NMR community for a long time. This fall into the name of chemical shift and anisotropy, spin rotation, intermolecular dipolar coupling, out of pair dipolar coupling, scalar coupling of the second kind, paramagnetic, and so on. Now, what was not new is obviously how this single state relaxes. So how these mechanisms are written when we talk about the long-lived spin state rather than the conventional longitudinal or transverse magnetization, right? So my first task when I was a postdoc with Malcolm, it was to go one by one into this mechanism and trying to devise a theory and eventually an analytical equation for this. And here it's just a summary of this equation found for the different mechanisms. And at the top there, you see basically the singlet. Actually, here it's not the lifetime, but it's actually the inverse. So the rate of the singlet, with regard, the top one is with regard to the intrapair dipolar coupling is 0. This means that they are immune. And then there is a series of equations here, which basically show the behavior of this state with respect to all other mechanisms, so at least the one that are in this table. Now, what we learned from this? Well, we learned that we could do a sort of intelligent design of the molecule and try to build in the knowledge of these equations, minimize all the terms, all these other minor effects, with the purpose to have longer and longer lifetimes of these states. So here is an example, still the one which detains the record in our institution here, which basically where we have the couple of spin 13, which may make the basis for the single states. And then eventually we have like the environment of spin pair conformationally inflexible. This is to reduce like spin rotation decay. And then there are like small chemical shift difference between the member of the pair. So we break the symmetry by only very little, so to avoid that mechanism. And then if you go around, you can read all the other, say, criteria which were built in, and a molecule should have to have longer and longer lifetimes. And if you want a number for that, then how long is long? Then here is this molecule, which has been measured in acetone. And you can see from the number down here, the T1 of this molecule is about a minute, slightly more than a minute, but the TS is longer than 70 minutes. That happens in acetone deuterated. So you can gain a factor of about 60 over the T1. Now, this is, you can see, this is like a sort of artificial molecule. We had to, well, we prepared them on purpose, but there are a lot of natural occurring molecules which have, which satisfy partially this criteria. So they have long lifetime in the sense they are longer than T1, but how long obviously depends on how well those criteria are satisfied. Another interesting example is the N2O. In this case, is N15 label, where we have a lifetime of 3 seconds for the longitudinal magnetization, 3 minutes for the longitudinal magnetization, but we have about half an hour for the lifetime of the long-lived spin states. Right, so, well, okay, so I would like to show you some, what we do with the states, but before that, obviously, we need a sort of toolkit. And the toolkit in NMR is essentially, well, it could be obviously equipment, and I'll show you some equipment later on in the talk, but mainly it's pulse sequences, so the way we manipulate spin order, essentially. And I have to say, over the years, so now it has been almost, I think, 20 years now since the Malcolm proposed this idea of long-lived spin states. And there were a lot of our groups, Malcolm's group, obviously, at the beginning, and then my group and other groups developing pulse sequences to play with these states. And there are a plethora out there. So these are known as M2S, SLEEK, adiabatic SLEEK, APSOC, ADAPT, generalized M2S, symmetry adapted M2S, and so on. Among all this family of pulse sequences, the one in the M2S family, they are the most versatile, at least to my judgment, not only because they come from here, but mainly because they could be adapted to experiments where you play this sequence along with pulse field gradients. So they transport these ideas into the field of diffusion and MRI, as I'm gonna show you extensively in the rest of the talk. So here it's one of this category, the M2S sequences, which basically takes some transverse magnetization at the beginning, performs a pulse sequence, so a series of pulses, which is built upon like series of echoes, with a number of echoes, and echo delay are carefully timed with the parameter of the spin systems, and then gives out singlet order. And then there is the time reverse of that, which is the S2M, takes singlet order and converts back into transverse magnetization, right? Now, while you can do the first transition, so from transverse order to singlet order with efficiency 1, so you can take all transverse orders into singlet order, we have to be conscious that the inverse, so going from singlet order to transverse magnetization, can only be done with a maximum convergence efficiency of 2/3. So you trade away 1/3 of the signal, but obviously you get something like 10 to 60 or more times longer lifetime. So depends on what you want to do, obviously, with that. Now, I mentioned why I like those sequences, apart from the fact that they were developed here, is that they can easily be transformed into spatially selective one. So by playing, by introducing shaped pulse and the usual stuff, so gradients and refocusing gradients and so on, you can now make the same transformation, but only in selected location of space. So the S2M at the top there basically takes transverse magnetization, produce singlet order, but only on a selected slice of the material. And the bottom one, again, does the same transformation from singlet order to transverse, but only on selected location of the sample. And again, it's also very easy to modify those sequences and make them diffusion compatible. So I'm sure people are aware about the way we measure diffusion. There is more about that later in the talk. But essentially, you create some you mark the spin position with some sort of gradient, often a bipolar gradient, and then you let spin diffuse, and then eventually later you reconvert the magnetization into some observable while decoding the spin position with another pair of bipolar gradients. And you can do the same within the M2S sequence. So you can basically develop pulse gradients M2S and pulse gradients S2M. And this is what we have done in this pulse sequence here. So, well, okay. So in principle, I'm ready to show you something. But I would say so far, I've just highlighted that the singlet order, it's long-lived or long-loved in that case. But maybe I would like to stress and everyone to be aware of the fact that there are two other important properties of singlet order. One is that it is silent in the sense that it's not a magnetic state, it's a spin zero state. So it doesn't give an NMR signal on its own. And also, it is accessible on demand. Essentially, we will have to transform some form of order into singlet order and vice versa. And we can do that with very selective pulse sequences, which do that either in some location of space, but also in certain spin system, because the sequence is adapted to the numbers, right? So the J coupling and the chemical shifts or whatever else is in the essence of the actual molecule we have in front of us. Now, if you combine these three things together, you could see that what you have in front of you, it's what would be called a long-lived smart tag, right? So it's a tag because you can follow it across, long distance or long time, but it's smart because you can actually access it only when you want. So essentially, my group now specialize in exploiting these smart tags in magnetic resonance experiments of different kinds. And here is a list of applications which has been developed over the years by us and as well as other colleagues. So for example, we have been using those states to store hyperpolarization, have a new form of contrast in MRI, track molecules over long time and long distances, measure slow flow, and all the way down the list. And as you can see, there are like pieces in gray, which is something I will not have time to talk today. And the pieces in dark gray is something which I will touch on in the rest of the talk. So I hope this make a good prologue to what is coming. And we'll stop here, but I remind people that in 2020, I've edited a book which contains, which discuss the theory behind that, the design of molecule, or the pulse sequence developed up to that time, and also the application of singlet order. So I invite people who want to read more about that to look at this book and read more and hopefully contribute to the field, which I hope I will show at the end of the talk is an exciting one. So moving on now, I'm going to select a few of those applications. I would like to show you how we deploy this knowledge and this pulse sequence and molecules which have been designed to support these states to perform these tasks. And obviously, the first one which came to mind to us, and I'm sure to everyone in the audience, is, well, if you have something living long, why don't you store hyperpolarized spin order? Because we know hyperpolarization is created by it's basically suddenly lost within a few T1s. So the idea of polarization, at least in my mind, could be thought as in this way. You have this bath of thermal polarization that you have to build into the system, right? And this is usually done by placing the spins into a magnetic field at some temperature. And this is what is called thermal magnetization, right? So longitudinal magnetization if you want. And then you can imagine the techniques developed over the year, which we call hyperpolarization, as a sort of pump, which take from withdraw signal, more or less, right, from the thermal magnetization and deposit it into a vessel. And this vessel is as a tap, so we could withdraw from this. So we have like a higher signal if we do experiment from this bath rather than from the thermal one. But we don't have to forget that there is a leak to this recipient, and that leak is essentially the T1, right? So it is sized by T1. So the faster the T1, the faster you lose the fluid you have pumped through this top level. Well, the singlet, you can imagine the singlet act as a sort of tighter container of hyperpolarization. So you pump the hyperpolarization in another container where you can take you can take some signal out of, but they have a leak again to the thermal bath, but that leak is much more smaller. Now, the interesting things at that point when we realized that was, can we make it even better than that? Can we actually include an idea of recycling? In other words, can we actually collect whatever it's leaking and then put it back in the hyperpolarized spin order recipient? And the idea came actually as possible, and we did this experiment in collaboration with Jan Erik and Kier Larsen in Copenhagen at that time. And I hope the idea will be explained in this pulse sequence here. So essentially, you take a molecule which has a long-lived spin order. So the number for this molecule are down here. The T1 is 45 seconds. The TS is about, well, it's more than 15 minutes or so. And this is what I would call the container, right? So then you can take this container into the dissolution DMP machine of Jan Erik and create some hyperpolarized spin order. Now that spin order will be lost within a few T1s, so literally a few minutes. But what you do immediately, you can convert into long-lived spin order by running an M2S pulse sequence. So out of the dissolution DMP machine, you take the order into singlet order, and now it could live up to half an hour or more. And obviously, so you have time to wait and do whatever you want to do with your sample. And at some point, you would like to detect. And the detection, obviously, is the step which could, in principle, kill, right, the signal. But if you want to recycle it, you can make this. You can convert it into magnetization, okay, in full, or at least as much as you can within the limits of the two that I expressed before, and any other sort of limitation coming from imperfection of pulse sequences and so on. But once you are in the magnetization, then you can actually observe it. And I suggest during this observation, you do a double echo and collect 4 FIDs. And then at the end of the FIDs, which you, by the way, you can sum up and have also a factor of 2 in signal to noise and give you like the answer you want about the spin system, then you end up having magnetization. But this magnetization is still hyperpolarized. And it's also still, and you are able still to bring it back into the singlet container. So that's what you do with an M2S. And once it's in the singlet container, you can store it there for a longer time, and eventually later come back to it, read it again, store it, and come back and read it again, and so on. Now, it looks like a nice idea, but is it true? Is it possible to do? Well, we did the experiment in Yarek lab in 2013, actually. And here you see the decay of the the long-lived spin order, which is alive for even after half an hour. If I remember correctly, unfortunately, I don't have the number here. The signal to noise is of the order of a few thousands after 5 minutes, and it's still 60 after half an hour. Now, you clearly understand that even the very first spectrum here won't be there if you use conventional methods. So if you store the hyperpolarized magnetization as longitudinal order, because the T1 was 44 seconds, so after 5 minutes, you nearly have nothing. So here is a method to preserve this, basically for as long as many minutes, in fact, hours, with those intelligently designed molecules. Well, but then we also thought, well, if you have a new decay constant, you probably have another mean to get contrast between different parts of an object, different tissue perhaps of a body. And indeed, we try to do this experiment. And it turns out that there are molecules for which there is a huge contrast in TS, whether the molecule is exposed to, well, the solution is exposed to oxygen, which is a paramagnetic substance, or not. You can think that could be also related to difference in pH or difference in whatever else condition surrounding the singlet molecule that you may compart for that particular application. In this particular application, as a demonstration, we took this molecule fumarate that we had around in the lab, and we knew it was a nightmare to deal with, because basically, if you look at the number, the T1 is 35 seconds if it's degassed, but only 6 seconds if it's not degassed. And the TS is 5 minutes if it's degassed, but only basically the same as T1, or 8 seconds, just slightly more if it's degassed, if it's not degassed, sorry. So it's a molecule where oxygen probably can get very close to this pair and destroy the singlet order as well as the longitudinal order. So, well, this is a perfect example for contrast, right? So what we did simply is we took a tube into another tube. The inner tube contains a solution of this fumarate diester, which has been degassed. So we expect 35 seconds of T1, 300 seconds on TS. The outer one has not been degassed. And the experiment here is very simple. So you create some singlet order through the M2S block. Then you wait some time. And then you have this T00 filter. I'll come to that in a moment. And then eventually you convert back singlet into magnetization. And then with a 90, you have, again, longitudinal order. And this means that you can now start any imaging sequence you want. In this particular application, we use equal imaging to do like fast MRI, but later you will see rare. You can use any other pulse sequence, or imaging pulse sequence you want, or the best one for your sample, in fact. Now, the T00 filter, you will see it from now on, you will see it in every sequence. That is basically a combination of pulses and gradients, which basically destroy everything else is not a singlet. So it's basically, if the M2S creates byproducts, these are destroyed before they actually compromise the whole experiment. And it's always present from now on. What you see in the images below is actually this experiment run at different time, at different values of the tau time. And you see the signal, so the image from the outer tube start disappearing, to completely disappear after 12 or 16 seconds, while the other one can be seen, the one from the inner tube can be seen even after 5 minutes. So you created that form of contrast through going through the singlet order rather than T2 or T1 contrast as usual well known, right, in MRI. Okay, well, then the other thing I showed before was about combining these sequences with bipolar gradients and diffusion-like techniques to measure diffusion. But before I go into that, I would say we have here a chance to actually observe molecule in the real space and image diffusion as it happens in other way, to track molecule and figure it out where they moved after a while, right? Which is basically imaging macroscopic diffusion in real space. Now, to do this experiment, you have to use this spatially selective M2S sequences. So the way you do that, you prepare some transverse order with a selective pulse played along a gradient, right? And then you transform that order into singlet only in that selected slice of the sample. Then again, you wait some time if you want. Then you filter out everything which is not a singlet, or everything which is a singlet, actually. And then non-selectively, you convert all the singlet order into magnetization, but wherever the molecule is at that time, right? And now this gives you, like, again, magnetization, right? With some sort of intensity everywhere the molecule has moved. And you can picture that with an image. Again, in this case, an EPI will do. So the experiment ran as follows. So here you have like a 10mm tube. This is this image here is just for reference only. Okay. Then if you do one of this experiment in which T is essentially 0, then you can see the slice of, I think, 3mm sagittal slice I selected in this experiment in the first part of the sequence. Now, obviously, in that much microseconds, the molecule haven't moved significantly. So when you come and take the image, you just see the molecule in the original slice. But if you now allow 1 minute, 2 minutes, 3 minutes, or 5 minutes, or whatever else time you have, depending on the molecule you're using, then you can picture the molecule right in the new location as they have moved. And the simulation below, done within Mathematica by an algorithm programmed by myself, then you can see that is exactly what you should see compatible with the diffusion time of that particular molecule and the time you have waited. So here it's a method to track molecule displacing right from the original position and moving into a different one after basically a long distance, or if you want, after a long time. On this note, another interesting application came as a suggestion originally from William Price in Australia, in Sydney, and then we teamed up with William. We did something together as well in terms of Q-space diffraction. So Q-space diffraction is a technique in which basically diffusion experiments are used to figure it out geometrical information about pore sizes or similar, let's say. I think one of the most notable experiment is you have a cavity, a rectangular cavity, and you'd like to measure the distance between the two walls. So you can do that with this experiment you see here, which is a conventional stimulated echo experiment, right? Which is very conventional experiment for diffusion. And if you basically plot the signal against what is called Q, which is essentially a combination of the duration of the gradient, the strength of the gradient, the gyromagnetic ratio, you see minima, which in this plot, and these minima occur at every Q, which is actually the inverse of the distance between the two walls. So essentially the molecule moves, hit the wall, comes back, and in this motion they have a sort of diffraction-like pattern. That diffraction-like pattern reflects, right, so repeats itself every other inverse of the distance of the walls. However, if the cavity is too big, in this simulation here, the cavity was supposed to be 400 microns, and you have even 10 seconds of diffusion time, you barely see anything in the diffusion plot. You need to have like 20 or even more seconds, right, of diffusion time to highlight this and measure. By measuring this dip, you essentially measure the cavity size. And obviously, it is clear you can't do these things with conventional diffusion, but you can if you enhance the diffusion time through singlet order, right? So the experiment is again, it's basically this time, you use this pulse gradient M12 sequence to create singlet order, but mark the molecular position at some time. And then after a long diffusion time, you decode the molecular position, and you also convert the singlet back to detectable magnetization with the PG S2M. And in the experiment here, I've used two cavities. These are like glass rectangular capillaries, where the inner cavity is either 0.8 or 2 millimeters, so it's really macroscopic. And the plots here, the dots here are actually the results of the experiment, and the line is the best fit. It's actually the fit. It's actually not the fit. It's actually the overlap with the theoretical equation you saw before. And as you could see, you can correctly measure these cavities, even if they are too big for conventional diffusion experiments. And since we are talking about diffusion, why not to use singlet to enhance also diffusion tensor imaging experiment? By the way, I forgot to say that the experiments you saw before, and this one and the one coming next as well, they all fall into what I called, with the worst probably acronym ever, SAD NMR, which stands for Singlet-assisted diffusion NMR. So within this name, they fall, there's a number of experiments which fall, including like measuring of flow and things like that. Anyway, so let's go into diffusion, then tensor imaging. Now, I think so far I've mentioned we can measure diffusion coefficients, but diffusion coefficients is not really the right word. We all know diffusion is actually a tensor. And it's actually it's a rank 2 tensor, so there are like in principle non-independent diffusion constants, but the tensor is symmetric, so only 6 of them are independent, in fact. Now to retrieve the shape of the diffusion tensor, right? One way is basically to constrain, to restrict the molecule into some geometry of some shape. The shape itself gives a shape to the tensor, to the diffusion tensor, because diffusion becomes different in different direction of space. However, there are some key concepts here. The molecule, after they do this random motion, they have essentially displaced, they have moved, right, a given length. And that length is proportional to the diffusion coefficient, but also to the diffusion time, so how long you let them diffuse for. The geometry itself has some characteristic length. This is an example of a cylinder. For example, the length could be the radius of the cylinder, but depends on the pore geometry, obviously. If it's a sphere, it's the diameter again, and things like that. Now, if the diffusion length is smaller than the characteristic length of the structure, so the molecule never touch any wall, right? So they don't experience any confinement. So the tensor is basically spherical, so all the eigenvalues are equal, and you can talk about the diffusion coefficient, which is essentially the 1/3 of the trace of that, right? So the isotropic value of that tensor. However, if you can restrict the motion, or if the motion is restricted because the geometry is such for that, or you can increase the diffusion length, so the diffusion time, so that the molecule starts exploring the restrictions, then the tensor acquires some degrees of linearity or n-planarity. Okay, now because delta it's limited by T1 in conventional NMR diffusion studies, then the structural information may be misrepresented in structure where the diffusion length is much smaller than the diffusion structure. So essentially, you may think the molecule is in a spherical environment, but it actually is not. You just didn't give it enough time, right, to the molecule to explore the geometry of the structure, right? And now, very shortly, how we measure the diffusion tensor, where you have 6 independent diffusion constant to measure. So you do like 6 diffusion experiment along 6 independent direction, and then you fit them. You get one of these curves every time. You can fit them all together to get the 6 different diffusion coefficients, which you use to build this tensor, which is basically the diffusion in the laboratory frame. Then you can diagonalize it, so you get now diffusivities along the principal direction. And the eigenvector are actually the diffusion, the direction where the diffusion has these diffusivities, right? So the preferred direction of diffusion. You can visualize that, and people do that. It's nothing that we invented, obviously, it's been there for many, many years, through to what is called the diffusion ellipsoid. So you basically build an ellipsoid whose direction of the axis follows the eigenvalues of the diffusion tensor, and the radii are proportional to the diffusion, or exactly equal to the diffusion coefficient in that direction. If you want, you can also convey this information in one single number. That number is usually called fractional anisotropy. It's very much used in MRI. And that number goes from 0 if the diffusion tensor is spherical to 1 if it's highly anisotropic. So the experiment we could do in this using singlets, so how we enhance the DTI experiment is, again, the same experiment we used before, but now run along 6 different directions of space. We collect this data, and then we use standard techniques to process those data and retrieve the diffusion tensor, diagonalize it, and blah, 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 all the things I show. The sample here I've chosen to demonstrate that are, well, of course, you have the sample, which is the container, the singlet container, which is the molecule down here in this corner, right? But then we would like to infer some information about the structure containing, containing this molecule. And we fabricated some phantom, which are made by plastics. We drill some holes. The holes are quite big, it's 1 millimeter, so they are. You can't do this experiment with conventional DTI. And we also had another version of these holes, which are tilted 30 degrees with respect to the laboratory frame Z axis, which is the axis of the magnetic field. So in doing that, you could see, so here is a series of experiments in which we basically vary the diffusion time, right? And we measure the diffusion tensor, and then we retrieve the fractional anisotropy, and also the angle between the Z, the principal Z of diffusion, and the axis of the molecular, and the magnetic field axis, okay? Which is also essentially the alignment, right, of this, which is the angle basically between the main axis of the holes here, right, and the magnetic field. And as you can see, if you don't allow enough time, you don't get the correct fractional anisotropy, but you also don't get the correct angle. Only when you have like 30 seconds or a couple of minutes or 4 minutes, you start to build up the right fractional anisotropy and figure it out the right angle, right, of inclination of this chambers, right, with respect to magnetic field. And the thing is even more evident where we know that the channels are tilted by 30 degrees, and you don't get that angle until you get very long diffusion time, as expected, obviously, from what I was saying before. But here it's like a way to enhance DTI and look at the structure of this information, right, even if the container are macroscopic. There is another thing you could do, and it's actually quite important, as we will see in a moment, on a number of practical porous media, and this measuring tortuosity through Singlet-assisted diffusion NMR. So you can imagine this. You have like a porous medium. Okay, here it's just a sample of packed bits, right? But it could be anything really. And obviously there is, if you take 2 points, 2 cavities, A and B, the tortuosity is how difficult it is to go from A to B, since you can't go in a straight line, and the molecule have to go through, you know, whatever is the interconnection of the pores within that structure, which is something natural. Now, it is known that you can retrieve this tortuosity value by taking the diffusion, measuring the diffusion a long time and divided by diffusion a short time. And this is called, the ratio is basically the tortuosity of that. Now, obviously, to do that, you need to have access to this restricted diffusion coefficient at infinitely long time, okay? Or what the matter there is obviously having enough time for the molecule to go out from one pore and and move through many pores, right? And explore the whole geometry, which obviously requires time. And this time is granted again by this experiment. So the experiment is again the same as before, but what you do here, you take a series of diffusion measurements, and as a function of the delta, so of the diffusion time, you plot them down, and what you see, what you expect is that these points flatten up, right, to an asymptote, and this asymptote is actually the tortuosity. For a sample of packed bits, this tortuosity is actually known. It could be calculated through algorithm. And this is what is shown here by the dotted line. So as you can see, in any case, so these are like 3 cases in which there are like different bits size. So the pores and the system of pores is different every time. And when we do the experiment and we let the molecule diffuse up to 4 minutes, we reach, in all cases, we reach this asymptote, which matches what is expected to be. Now, moving on, actually, in fact, moving on the same line, right? I'm going to talk about the very latest topic today, which is field cycling Singlet-assisted diffusion NMR. So one can think about, well, okay, let's put those things in practice. Okay, where tortuosity matters. Where tortuosity matters, for example, in the field of batteries. There is a lot of porous stuff which they use in batteries to separate things, right? And molecules have to move across those pores. So it's important to see how tortuous is that. And there is also an even better and more interesting, at least in my group, field where this could be interesting. It's if you start cultivating cells in a 3D printed support, the cells infiltrate the scaffolds and they close up the pores. So progressively, you have an increasing tortuosity, right? Can we track that? This is a very strange heterogeneous sample, which is basically heterogeneous in time because things grow with time, and also in space because they also grow in different parts at different times, right? So very interesting sample to work with. So now one can think, okay, you have the tools, just apply it. Well, actually what we didn't really appreciate at the beginning was this. We know that the plastic there will bring some susceptibility in homogeneities. The susceptibility in homogeneities will bring big gradients. But then we said, well, very good. Singlet is insensitive to gradients. So that would be even a plus with this application. What we didn't consider fully at the beginning was that obviously spins diffusing in these pores, they have a sort of a fast T2 relaxation mechanism. And now we have no time to play the echoes, so to play those false sequences to get into the singlet order in the first place. So somehow the singlet is long-lived, it's insensitive to these gradients, but you don't have the time to do to prepare it. So then we want to study this phenomenon and do something to counteract it. So the way to study that is a bit long. I'm going to cut it short because I'm conscious the time is running out. But basically what we want to do is to take a real image, to build some coding, by the way, some simulation coding that we succeeded in that, which takes the actual structure of your porous medium through a micro CT image, okay? And then knowing where the molecule can move, we can build the magnetic field, okay, which is called the 3D magnetization of field. So know the magnetic field point by point in that structure. Let the molecule do a random walk and move across all the pores. And now we know the field experienced at each instant by the molecule passing through that particular corner of the structure. This is the fluctuating field here, you see here. When you learn actually relaxation in NMR, you have been seeing like the relaxation is caused by fluctuating field. This is a way to track those fluctuating field experienced by molecule, in this case, diffusing into a molecule which has susceptibility in homogeneities in the magnetic field, okay? And now we use this, a little bit of theory and so on, and we could build a numerical and in some cases also a well-known solution, an analytical solution, to calculate how long the T2 of the spins is, right? When they move in a field of, in this case, 1 Tesla, alpha Tesla, or 0.1 Tesla. And obviously, it's very straightforward what you should expect. The lower is the field, the lower is this phenomenon, because at the end of the day, it's all about this, the product between the magnetic field and the susceptibility mismatch, the delta chi. Okay, so how do we actually perform experiments where the field is so low that this is, then you don't have this inhomogeneity problem, but then you don't lose, right, the signal, and you don't lose sensitivity, and you don't lose like resolution. Well, the way we thought that could be done, it's in a field cycling fashion. So we went on building a shuttle and a 2-core magnet. You see a schematics here. There should be an animation down there, where we basically have 2 probes. We have the top probe tuned at 500 kilohertz, placed at 46 millitesla, where the carbon resonates at 500 kilohertz. And then we have all sorts of hardware, including some shimming, where we and also 3-axis gradients in low field. So we can basically now pulse, radio frequency pulse, and also 3-axis gradient in low field, and we can polarize and also read the sample in the high field, so retaining resolution and sensitivity. So here it's some experiments, and I'm going to stop literally in 2 slides. So the experiment you could do with this kind of thing. So first of all, the dual core machine is actually general. You can perform any sort of 2-field experiment, okay? So for example, you can measure T1 in low field, right? So you just have to adapt your sequences to work in these 2 in these 2 fields. And in this particular case, we have a molecule trapped into a sample made by beats. We measure the T1 in low field to be 20 seconds. You also can adapt the M2S sequence to work in in this 2-field regime. And we measure the lifetime of this molecule in the beats in low field, which is about 5 minutes, as you can see in this case. The purpose of all, obviously, is now to get access to the diffusion, right, in 3D. So you need this 3D capabilities, which is actually unique. There are many shuttles in the world, but this is the only shuttle which can do that, so which retains radio frequencies, but also 3-axis gradients in low field. And here it's just an example of how we measure the diffusion in 6 different directions. We reconstruct the ellipsoid, for example, of that molecule moving across the pores left through this simple sample of packed bits. And again, you can do the same. You can measure tortuosity. And again, we retrieve the value, which is what is at the limit, actually, of what is said to be calculable with theory in literature. So I think that is probably all I wanted to say today. So I hope I show you a lots of application where we basically coupled the concept of longally spin state with the concept of pulse field gradients. And here it's a long list of collaborators. So I'll show things made by the current group. You see a picture of them around here. Some of them, they actually left the group very recently, past members, Andrew and Francesco, Monique, Turel, and Silvia, they all somehow contributed to what you saw before, other collaborators in chemistry, and so on and so forth. And I think I'll leave you with that. In fact, I'll leave you with the next slide, which reminds yourself that I've been active recently in publishing books. So there is a book about spin dynamics on the left there, but very recently, just in February, I also published a book about the the classical mechanics behind quantum mechanics. So if anyone wants to read about that, they are out there from these publishers. And I'll stop here.
All right, great, Giuseppe. It was a really nice and very informative talk. Thank you so much. So for the audiences, if you have questions, please post them in the Q&A channel, and we'll select a few questions to discuss. Actually, we have a lot of time for discussion. Let me actually make 2 quick announcements. So in 1 week from now, that's May 7th, we will have the next Global NMR lecture by Tamara Wolf. So it's not in 2 weeks, but in 1 week, May the 7th. And secondly, I also want to remind everyone that we will have the online conference, the Global NMR online conference this summer. Please stay tuned for that. So I will start with a question. So in terms of designing the molecules, are there certain, let's say, directions or some rationales of the next generation, let's say, singlets being conserving molecules?
Yeah, exactly. Yeah. So essentially, we made a list of these criteria. In fact, they are in that book I cited before. So there is a whole chapter about that. I would say it's probably very quick to say that what you try to achieve, it's the so it's obviously to have like this spin pair, to isolate it from the closed space from other nuclei with spin. Often you have protons. Okay, so you think, okay, an easy way is to replace the proton with deuterium, but actually you have to be careful as well, because deuterium can induce scalar coupling of the second order relaxation, which could be also challenging. So, and then you want to protect, you want to kind of have a sort of rigidity in the molecule, so that basically the molecule doesn't flip around. This will generate some low torsion of low, low frequency, which also induces a spin rotation like mechanism. Okay, we call it spin molecular rotation, but never mind. So there are mechanisms of this kind, and then I think another important thing is trying to protect it from the approach of other paramagnetic molecules you may have in solution. One above all is oxygen, but also you may have other contaminants, right? Really that. So it's all about that, let's say. So there are many molecules we have done. I mean, we have a full book. We have a good collaboration with chemists here. It's probably, we have maybe 50 or so molecules of different. Basically we at each molecule we learn more about that mechanism, and then we made the next one to be longer and long. So what you see here is just the end, more or less, of that chain. What would be interesting now is for people to pick up this and make it perhaps biologically active, you know, or encapsulate some functionality, you know, sensitivity to, I don't know, pH or whatever makes it interesting for application, right?
Yes, I agree. I mean, I feel to some extent it's kind of similar to designing a molecular qubit. You want a system that is sort of well isolated from the environment, and also preserving certain properties. So in your mind, is this, let's say in the future, the designing of the molecules, would it be a more kind of a screening approach to just look through a vast library of molecules, or more kind of build upon the knowledge you learn little by little, or kind of see different categories of molecules and then identify which might be the best suit?
Yeah. So I would say this. I think from my experience, is this. If you work with protons, so you have like a proton spin pair, you are always, so the protons are usually very exposed in the molecule. They have all sorts of interaction with the solvent and everything. So you never, you won't find like hours long lifetimes, at least not, you know, we haven't found any like that. I think there are good reasons to justify that kind of sentence. You would like to work with core nuclei and possibly with low gamma. The low gamma itself, right, protects you in the sense because every interaction is scaled by gamma, right? So you have suddenly you have like a factor to gain, you know. So if you are concerned about J coupling to a nearby spin, right? If your gamma is low, then the J coupling is also lower. So essentially, you may want to go that way. But if you go that way, then there are other concerns, obviously, right, to keep in mind. And I would say, and then somehow you may want to kind of label those molecules. So the process of intelligent design, it's important because it can give you like shortcuts, but there is still like a lot of synthetic chemistry involved. Techniques like hyperpolarization can amplify the signal of natural abundant spin pairs. And we have already suggested many times that that should be picked up and used to identify molecules with long-lived spin states. I think this is only I only see very few examples of that in the community. Unfortunately, at the moment, we don't run hyperpolarization in our here in Southampton. So we can't do it ourselves, but you know, we have already put that in many congresses. We have taught to people and say, you know, if you could do this experiment, I think there is something interesting then to learn.
Great. So we have a question from Florian. Hi, Giuseppe. For the 3D demagnetization field simulations, what is the relation between the strength of the fluctuating magnetic fields and the distance from the pores?
Yeah, right. Okay, great. Yes, great question. Hi, Florian, by the way. No, so essentially what we capture here, so what I plot here, it's in fact the fluctuating field against time, right, across the all trajectories. The trajectory is actually 20 seconds. So you see the molecule goes everywhere. But actually what we really have, we have a vector which contains the position of the spin, right, at each time. So we can actually, we basically go and eat the walls and reflect back as well, right? So we have all sorts of sensitivity to the location. So the magnetization field is as precise as the structure, because what we do, we use like a Fourier convolution, right? So we build one demagnetization field, which is a dipolar field in the middle, and then we use the Fourier transform, well, the Fourier convolution theorem, to have in each point in which we have a point in the image, and those points, if I remember correctly, for this approach were like 3 microns resolution. So every 3 microns we have like a point in the micro CT, right? And every 3 microns we know the field, the field in that point. 3 microns, it's small compared to the size of the bits, which are usually of the order of 200 microns up to 1 millimeter, in fact, in our samples. Is that answering the question, Florian?
Yeah, okay, thanks. So
Great.
are there any other questions? So if you happen to be in the panelist and your audience, if you have questions, you can just unmute yourself and speak up. We got another question from Mohammed Sabah. Hi, Pep. Hi, Giuseppe. Thanks for your wonderful talk. I have a couple of questions. One, could you clarify what you meant by symmetry adapted S2S, M2S? And the second question is, have you explored accomplishing some of the wonderful experiments you showed on studies of diffusion using variants of symmetry-based sequences such as a pole?
Yeah. Okay. So hi, Mohammed. And so Mohammed is probably just nearby here. It's obviously here in Southampton. Well, okay. So symmetry adapted M2S, I actually meant your sequences. So the latest development of M2S. So the word M2S here, it's more general for transformation between magnetization and singlet. But what I really meant, I actually don't know the way you prefer to call them, but it's where we use the symmetry, right, to develop sequences where you can make the transformation between magnetization into singlet and vice versa. So that's what I meant. So literally referring to your own paper. And indeed, so the second question was about using those sequences into that. So obviously that was always a plan. And I think I at some point I even interact with you, right, and ask you about those sequences, but then taken by the development of the hardware. So I presented very quickly, but that double field machine, it wasn't simple to make, obviously. It involved actually Bruker as well to make parts, and lots of issues in there. So eventually we haven't done it yet. So we haven't used them. But indeed, I see no problems in coupling those. And we should do it really because your sequences perform better than the M2S you see on the slide now, which is the original, let's say, M2S.